Hi everyone, welcome to week 3. So week 3 will focus on chemical bonding. It's not about ionic bond, covalent bonds, and the metallic bonds that we learned in the previous semester, but in this sem, we're going to learn how to determine a molecular shapes in a 3D form and what is that super and semiconductors. Let's look at the learning outcomes. The first one is what is that resonance structures? All right, resonance structure usually a drawing structures that we can't actually use a Lewis diagram to explain it. Okay, so any molecules that can't be explained well using Lewis diagram, then probably it has a resonance structure, which I'm going to explain that in a couple of minutes. So next one is able to determine the shape of molecules and polyatomic ions based on the VSEPR theory, valence shell electron pair repulsion theory. Next would be to decide on the super coordinations of ionic lattice and sketch it. So ionic bonds arranged in the ionic lattice structures, and even though they are as simple as alternate arrangements of positive and negative ions, but then they still have different coordination numbers. Okay, we'll look at it in a while. And then next we'll be able to define and explain superconductors with appropriate example. Same goes for semiconductors. We might able to provide examples of semiconductors. I'm sure you guys learned about what is that semiconductors and what is n-type and what is p-type, right? So this is what we call a doping effect on the semiconductors. It's either increase the charge carrier, it can be a electrons, or it can be positive hole or hole, right? So the last one will be able to explain between n-type and p-type semiconductors using appropriate example, as well as what is that photovoltaic effect. All right, now let's look at it for introductions. How can we actually determine the molecular shapes? How can we decide how a molecule or atoms within the molecules arrange themselves in a 3D space? Now, to determine the molecular arrangements, we have to look at the central atoms of a molecules. Now, what does that mean by central atoms? Look at that, the first one. So, carbon dioxide, CO2, right? So, the central atoms will be the one with the least number. In this case, the formula is CO2. Of course, the central will be the carbon. So, this is the one at the center, and then it's attached to with double bonds with two oxygens. Now, to determine the arrangements of the electron pairs or the molecular shape, we have to look at the central atoms and we have to count. We have to consider how many electron pairs or how many electrons surrounding the central. So in this case, carbon dioxide is supposed to have 4 valence electrons, right? 1, 2, 3, 4, and then it is shared with 2 electrons from each oxygen. Therefore, you get a double bonds from each side. So total, you have 8 electrons, and these 8 electrons, how are they going to arrange themselves? Because electron pair causes repulsions with another pair of electrons because they are all negatively charged. So they will arrange in such a way that to minimize the repulsions between electron pairs. All right, so that's why it resulting in all these different 3D arrangements. We have linear shape, we have band shape, trigonal planar, trigonal bipyramidal, T-shape, square planar, trigonal bipyramidal, and octahedral. Now, these are the shapes that we're going to learn and we need to remember. So, if a molecule is given to you, any random molecules, you must able to tell whether they arrange in a linear shape or octahedral shape. And it all depends on the central atoms again. Now, the basic things we need to do before we identify the shape, before identify the repulsion force, we need to know how to draw a simple Lewis diagrams. I'm sure you guys know how to draw a Lewis diagram. Lewis diagram basically just to, based on the molecules given, just to put in dot and cross or just dot to make sure that the atoms involved all achieve octet configurations. That's what we draw in the Lewis diagram. Let's say, for example, I have ammonia, right? Let's say examples, we have ammonia. So NH3, so nitrogen and 3 hydrogens. So this is ammonia molecules, and how can we draw the Lewis diagram? We know that this is a covalent molecules, so nitrogen should have 5 valence. So nitrogen, I have 5 valence electrons. 1, 2, 3, 4, 5, right? And then I have 3 hydrogens. So I put it aside with each electrons because I know they're going to share electrons with the hydrogens to form a single covalent bond, like that. right? Dot and cross, hydrogen has 1 electrons and nitrogen has 5. So this is how they bond with the hydrogens. And can we bond double bonds? Can we form a double bonds with hydrogens? No, because hydrogen has only 1 electrons and they need only 1 extra electrons to achieve a doublet configurations. So it's either doublets or octet, right? So in this case, can you see that I'm forming 3 share pair of electrons here, dot and cross, and these 3 we call it as bonding pair. Okay, bonding pairs. So I have 3 bonding pairs here, and then can you see that I have extra pair of electrons here from nitrogen, because nitrogen has 5 and it needs only 3 to achieve octet. Therefore, it takes out 3 to share with hydrogen, so nitrogen now actually having an octet arrangement. Let's count it up. 1, 2, 3, 4, 5, 6, 7, 8. It is stable. But then these pair of electrons, the pair of cross here, are doing nothing. They are not sharing, they are not bonding with anything, it's just free. So this is what we call an extra pair of electrons, and they name it as lone pair of electrons. Or in short, we just call it as lone pair. So whenever you have a pair of electrons doing nothing, we call that as a lone pair of electrons. Okay, so these are the things that you need to remember, the terms, like what does that mean by bonding pairs, and what does that mean by lone pairs. Okay, so let me erase that. I'm going to show an example here in the diagrams. Now this is the Lewis diagram again for ammonia. Right, now Lewis diagrams basically involve dot and cross or just dots. Now of course this is the typical Lewis diagram, and this one, it also can be a simple Lewis diagram, because we know that these 3 pairs are shared. So a shared pair of electrons, we can use a line to represent bonding pair. So therefore I draw lines here, and then accept this. This is actually the lone pair. Now whenever you see a molecule with a lone pair, they're actually capable of forming a dative covalent bond with another ions or atom. What is that dative covalent bond? What is this? Right? Now see, let's say I have A and B. I have 1 electrons for A, B has 1 electrons, so both of them can use their only electrons to share up, and then they form a covalent bond. Now a covalent bond is always a shared pair of electrons, is always a fair sharing. You take out 1, I take out 1, and then we bond it. That's it, right? This is a fair sharing. But what if we call that as dative covalent bond? When you see the word dative, means it is an unfair sharing, which means I have an atom or molecule with a pair of electrons doing nothing, which is lone pair, and then I have another atoms with 0 electrons. But A and B is going to form a covalent bonds. They are bonded together with each other. So how can they bond to each other where B has nothing to share? Therefore, since A has extra electrons, A will actually use its lone pair to form a dative covalent bond with B. Basically, they are forming a covalent bond as usual, but then this shared pair of electrons is actually belongs to A. Nothing to do with B, but A willing to sacrifice 1 electrons to share with B. And this type of covalent bond, we call that as dative covalent bond. Okay, dative covalent bonds, which is, I'm going to show you an example here. When NH3 has a lone pair, and then you actually have a hydrogen ions. So can these two bond it together? Yes, because ammonia has a lone pair, the nitrogen has extra pair of electrons, and hydrogen plus has 0 electrons. But then it's still possible to bond it together to form these things, NH4 positive ammonium ions. So this is how they form, right? Can you identify where is the dative bond? You see that we have blue and red, which means red is from nitrogen, blue is from the hydrogen. And then we have 1 odd pair here, both red. And this indicates that this pair of electrons is actually both belongs to nitrogen at first. And then nitrogen is so good that it sacrifices electrons, use the lone pair to form a dative covalent bond with these extra hydrogen plus. Therefore, you get ammonium ions. So this is what we call dative covalent bonds. And this is the basic of Lewis structure. Okay, so like I said, Lewis structure is a basic step, or it's the first step before we can identify on the molecular shapes, because we need to know how many bonding pairs, okay, how many bonding pairs surrounding the central atom, as well as how many lone pair surrounding central atom. And that will actually determine the molecular shapes. All right, now look, resonance structure. Now, like I said just now, some molecules are not so well described by Lewis diagram because in terms of electrons, they can't actually fully octet. They can't actually evenly shed. Let's say, for example, ozone layer. All right, we have ozone molecule. Ozone molecule is O3. Okay, let's draw it out in a simple Lewis diagram. Let's see what's happened. So I have ozone, which means I have 3 oxygen atom and bonded to each other. Okay, so how they actually bonded to each other? Let's say now oxygen should have 6 valence, so I'm going to take it out 1, 2, 3, 4, 5, 6, and the other oxygen, same for the rest, right? And same for the rest. So how are they going to bond it with each other? Obviously, oxygen need 2 extra electrons to achieve octet because 6 plus 2, right? So now each oxygen atom will take out 2 electrons to share with another oxygen atom taking out another 2 electrons. Therefore, each will actually share out 2 electrons to achieve stable configurations. But then, can you see that? This is oxygen A, oxygen B, and oxygen C. What I will see here is A and C both are actually having a stable configurations, right? 1, 2, 3, 4, 5, 6, 7, 8, just nice. And same goes to C. But then if you look at B, right, how many electrons there? So let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You have 10 electrons. You have more than 8 electrons, and for oxygen it is unstable because the best is 8 electrons. Try not to be less than 8 and try not to be more than 8. But then if that's the case, all right, we have to make oxygen A and oxygen C to be stable. So we have to form double bonds. And that will make the central atoms unstable because I have 10 electrons altogether. So this is not well described, like I said, by a Lewis diagram. This is actual Lewis diagram. So these molecules, to make sure that every single oxygen in the molecules are stable, they arrange in more than one Lewis diagram or Lewis structure. So that is what we call resonance structure. I'm going to show you how. Okay. So let's say I have the first oxygen here, and then I have 2 oxygens, right? So the first diagram is, let's say I have 6, not let's say, it has 6, right? So I'm going to do this, 6 electrons, and I'm going to take turn to form double bonds with one of the oxygen here, oxygen A, again, B and C. So I'm going to form a double bond with oxygen A first to make it stable. Okay, 1, 2, 3, 4. Okay, this is stable. Okay, this is stable. And what about C? C, we don't actually do that. We've used if we form a dative bonds with it, so we form a single bond instead. So how does it work is, because the purpose now is I'm going to make A stable but not C. So C, we still have to be bonded, right? So therefore, I'm going to use the pair of electrons just now to share with oxygen, and this is the dative covalent bond, guys. I'm going to share with it. And C itself will have how many electrons? Itself will have 6, right? These 6 electrons are not doing anything. They don't use any of its electrons to form bond with oxygen B. Oxygen B use its lone pair, a pair of electrons, to form dative covalent bond with it. So that will result in a structure like that. O, double bond O as usual, but that will give you oxygen with still have 6 of its electron, therefore is negative, and here it is positive because I'm using my own electrons to donate. So you may be confused now. How come they have there is a positive and negative charge? Look at that, guys. See, oxygen supposed to having 6 valence, right? So 1, 2, 3, 4, 5, 6. You see that these 6 electrons is actually given to oxygen C. Okay, I donate to oxygen C so that you can pair with me. Basically, I'm losing 1 electrons to oxygen C. Therefore, it is positive. And for oxygen C itself should have 6 valence. 1, 2, 3, 4, 5, 6. Just nice. But then what about this 6 electron? This is now belongs to oxygen C because they share. So now oxygen C should have 1 extra electrons from B. And these 1 extra electrons making it a negatively charged. And that is how you get the dipole, the positive and negative charge. Alright? And then, can you see that? The bond length is different. When you form a double bonds, the oxygens have a stronger attraction towards the pair of electrons because more electrons, meaning that you have to attract them strongly. So the bond length between A and B shorter compared with the bond length between B and C. You see that? So this is how they form one of the structure. And then just this is the one that making A stable, right? And then they form another one that they try to make C stable. So the whole thing will be flipped. Oxygen here as usual. Okay, now I'm going to make C stable. Oxygen C stable, so that you form a double bond on this side, but then you form a single bond, a dative covalent bond with oxygen here with a negative charge. 1, 2, 3, 4, 5, 6, and then this is positive and this is negative. You see that? So basically you are changing the positions of the double bond. And these two structure is interchangeable. The double bond can move to anywhere. They can flip the structure, right? So these two, structure 1 and structure 2, both are known as resonance structure. So only for molecules with lone pair and then with a double bonds. So usually when you look at the compounds, right, when you realize that I have at least 1 double bonds and then I have lone pair, so that's the case where they are showing resonance structure. All right, so this is what we call resonance structure, and the combination of these two, right, the combination of these two will give you a hybrid structure. Now what is that? Look at that. Measurements show that ozone has 2 identical bonds. What does that mean? It means ozone supposed to have 2 identical bonds with the same length. Wait, something just not right. Just now I was saying the one with the single bond is much longer compared to with the double bonds. And how come now under an instrument that measure it, the bond length are the same? Why? Because these two resonance structure, they combine together to give you a hybrid structure. And a hybrid structure should look like this. See that? I redraw it so it's clearer. Now, basically both having a chance to form single bond with oxygen B, right? Both A and C will have a chance to form a single bond with oxygen B. The only thing different is whether B is forming double bond with A now or forming double bond with C now. So the double bond is actually interchangeable between A and C. Therefore, since they are changing positions between A and C, I can use a dotted line to represent the position of the double bonds because the double bond is not fixed, right? The double bond is changing, sometimes A and sometimes C. So I use a dotted line to represent the possible position of the double bonds. And then still remember just now the structure. When there is a single bond here, it should be negative. When there is a single bond here, it should be negative. So now, since the double bonds are equally shared between A and C, the negatively charged should be in between them. Okay, of course this is still positive and this is negative. So it's instead of the negative charge on A itself or wholly owned by C, now they share because the double bonds are actually sharing between A and C. The double bonds are moving. So this is the reason why we got a identical bond length. Okay, so this is what we call a hybrid structure. So again, don't get confused between resonance and hybrid. Resonance is the different structure they form with different position of the double bond. Right? I make it simple. Whenever you see same molecule with different position of the double bond, it seems like the double bond is moving around the structure, the molecule. That's what we call resonance. And if you combine all possible resonance structure, you are getting a hybrid structure with a dotted lines like that. to show the possible positions of double bonds. So this is what we call hybrid structure. Okay, so basically, as a conclusion, in the resonance structure or in a hybrid structure, the bond length are the same. Okay, so therefore, when we do a measurement, when you have a double bonds, the bond length is the same, although from the resonance it seems like one double, one single. No, they are the same. So it means that the double bond is sharing. Okay, so these are further examples of resonance structure. You see that the position of double bond initially on the right hand side, and then now it turned into the left hand side, and the positive and negative will change position as well. So always remember, single bond is negative when you have a resonance, double bond is stable, it's the usual one. Okay, this is another reason you have a resonance structure. Look at that, this is position A, B, and C, right? That's where we can get to see that double bond. When you change into another structure, A, B, C, the ABC has no more double bonds. The double bond actually shifted. So where does it shift? It's actually shift like that, shift like that, shift like that. See that? So when you see a double bond move between two structures, no change in the structure itself, but just the position of the double bond, that's what we call a resonance structure. Same goes to the example here, NO3. Nitrate ion. See that? The blue double bond is on top, and then move here, and then move here. And when you combine them, you can get a hybrid structure. I'm going to show you one of the example here, how to draw the hybrid structure. Look at that. Let's take this as an example. What is a hybrid structure if we know we have two resonance structure like that? It's very simple. It's nitrogen as usual, and then you draw a single bond for both oxygen first, and then you draw a dotted line, indicates that the double bond can be in anywhere, can be on the left, can be on the right, and then this nitrogen is still positive, but then the negative is not on one side but in between them. So this is the resonance or the so-called the hybrid structure. And if you look at this, right, what is the hybrid structure of this? The hybrid structure of this will be here, nitrogen, single bond for all. I'll make it this way, all right? And then where will be the double bond? It can be anywhere. So I draw a dotted line here, dotted line here, dotted line here. You have 3 dotted lines, and these 3 dotted line indicates that the double bond can be on the left, on top, or at the side, and then the rest remain the same. Just follow back the same structure of the resonance, put a negative charge here, but this negative charge will be shared by all of them. Okay, all of them. So this is how you get a hybrid structure. All right, now let's come to this. Now we have learned about how to draw a Lewis diagram. Next, we learn about dative covalent bond, where you use your own electrons to share with other atoms, and that atoms contribute nothing to the sharing. All right, so this is an unfair sharing, so-called. And then we learn about resonance structure, making use of the dative covalent bond so that they can move the double bonds and all this, right? And now this is the time where we need to learn how a bonding pairs and a lone pair. Again, bonding pair is shared pair of electron. It can be covalent bond, it can be dative covalent bond. It doesn't matter as long as they're shared. It can be the lone pairs. These two, the number of them, will actually affect the arrangement, the 3D arrangements of molecules. Number 1, both bonding and non-bonding electrons. Non-bonding electrons here referring to lone pair of electrons. Okay, so bonding and non-bonding electron pairs must be considered. You have to consider them. How many? Let's say I have 2 lone pairs, 3 bonding pairs. The number actually make an impact on that. So the theory based on this, we call that as valence shell. This valence shell referring to the central atom only. Electron pair, the central atoms that has how many electron pairs? It can be bonding, it can be lone pair. Repulsion theory. So the bonding pair are repelling each other. The lone pair also repelling each other from the central atom. And these repulsions, they have to get rid of them. They have to minimize it. So they have to move away the bonding pairs far from each other. They have to move the lone pair far from each other. They have to move the lone pair and the bonding pair far from each other to certain angles. Okay, so that they can minimize the repulsions, and that will actually giving you different molecular arrangement of molecular shapes. And as an example here, look, first I am given with the molecule, this is given, and then step 1, what we need to do, draw the Lewis structure out. And from the Lewis structure, what we can identify here, I have 3 bonding pairs and 1 lone pair. And from the number of bonding pairs and 1 lone pairs, total, how many electron pairs actually surrounding nitrogen? I have 4 electrons pair surrounding the central nitrogen. And these 4 electron pairs will give you a certain electron pair geometry, which is this. This is the arrangement. They will arrange in such a way like that so that the repulsions between the electron pairs are minimized. So the bond angle here is actually 109.5. That will lead us to a molecular shape of tetrahedral, a name for it, okay, a tetrahedral. This is electron pair repulsion theory, right? So this is electron pair geometry. This is how the electron pair arrange. But if you go further, okay, this is step 2, guys. If you go further on, now this step 2, we only consider, okay, I have 4 electron pairs. In fact, right, the 4 electron pairs, one of them is actually lone pair, and the other 3 are actually bonding pairs. And that will actually lead you to another structure called, this is what we call molecular geometry, when we consider specifically how many lone pairs and how many bonding pairs. That will give you another shape of trigonal pyramidal, this name. And why is it so, you may ask? Isn't it they arranged themselves already in the tetrahedral shape? This is the arrangement with 109.5. This is stable already? No. Why? Because, look at that. WSCPR states that lone pair repulsions is the greatest. Okay, the repulsions between lone pairs are the greatest, followed by more than lone pair bonding pair. And this is still greater than between bonding pair. You get what I mean? Okay, so lone pair repulsion is the greatest. When you put 2 lone pair together, it repels further. The repulsion force is greater. When you put 1 lone pair and 1 bonding pair together, the repulsion, yes, is in between. It's not as great as between lone pair, but it's still quite a big repulsions. And the third one, the one with the least repulsion, is still repel, but compared to the rest, is the one with the least repulsion will be when you put 2 bonding pairs together. And because of these, the variations in repulsion forces, repulsion strength, that will make a difference if we have 3 bonding pairs with 1 lone pair compared with just 4 bonding pairs. Do you get what I mean? So both are actually, see, if we compare these two, 4 bonding pairs, I have 4 pairs of electrons, obviously. 3 bonding pairs and 1 lone pair, again, I still have 4 pairs of electrons. But these two looks the same, but they arrange in a slightly different molecular geometry, because whenever there is a lone pair, the repulsion will be greater than just pure bonding pairs. So that will lead us to different molecular arrangement. Okay, so next one is the example of electron pair repulsions. So these shapes are just consider number of electron pairs without looking at how many of them are actually lone pairs, how many of them are actually bonding pairs. No, we just look at, okay, I have how many pairs of electrons, just tell me that, and then I give you the shape, I give you the arrangement. So this is the one, look at that. If you have 2 electron pairs, regardless of whether lone pair or bonding pair, guys, it will arrange in linear. If you have 3 electron pairs, it will arrange in trigonal planar. If it is 4 electron pairs, it will automatically be in tetrahedral with the respective bond angles. And then if it is 5 electron pairs, it will be trigonal bipyramidal. If it is 6 electron pairs, it will be octahedral. I always read different pyramidal and bipyramidal. If I make a mistake, please, remember that. So this is trigonal bipyramidal and octahedral. So this is how it looks like with the respective bond angles. This is purely arrangement of electron pairs. Now, what if we consider molecular geometry, which means we have to consider now, out of the 5 electron pairs, let's say for example, out of the 5, how many of them are actually bonding pair and how many of them are actually lone pair? If that's the case, it will lead us to even more different molecular arrangement. Okay, so this is a simple calculations that show us to identify the number of electron pairs. Let's say for example CH4. Okay, we look at the central as usual. Central atoms has how many electrons? I have 4 valence electrons for carbon. Refer to the periodic table. And how many atoms actually attach to carbon? 4. So 4 plus 4. And then you divide by 2, you will get 4. So basically you have 4 electron pairs. And of course, guys, from these calculations, you won't be able to tell the 4 electron pairs are either bonding or lone pair. We can't tell until we draw it out. Until we draw the Lewis diagram, then only we can tell. This calculation itself will only reflect to us that this molecule, the central atom carbon, has 4 electron pairs. If it is just 4 electron pairs, what will be the geometry? Let's go back to the previous slides. 4 electron pairs will be this, and they will arrange in tetrahedral. CF4 will arrange in tetrahedral in terms of electron pair geometry, just electron pair. But what if we are considering lone pairs and bonding pairs? That will lead us, like I said, even more variations in terms of the shape. Look, we look at these two. If you have 2 bonding pairs and no lone pair, that will be linear. But if you have 3 bonding pairs and 0 lone pairs, that will be trigonal planar. If you have 2 lone pairs and 2 bonding pairs, 1 lone pairs, you will get a band shape. I know up to this stage you're like, oh my goodness, am I going to memorize all of them? I mean, in a way, yes, you need to know the number of pairs that you have. In terms of bonding pairs, okay, how many bonding pairs we have, how many lone pairs we have, it will lead you to different molecular geometry. Alright, so remember that 2-0 is linear, 3-0 is trigonal planar, 2-1 is actually bent, and followed by 4-0 is tetrahedral, 4 bonding pairs, 0 lone pair, 3-1 trigonal pyramid, 2-2 band shape again. Alright, and what if you have 5-0 trigonal bipyramidal, 4-1 seesaw, 3-2 T-shape, 2-3 linear. So this is for bonding pairs, and this is always referred to lone pair, guys. Don't get confused, although they use different terms. 6. I have 6 electron pairs, and none of them are lone pairs. It will be octahedral. But out of the 6, right? What if one of them is lone pair, another 5 are bonding pairs? Then it's square pyramidal. And then what if you have 4 bonding pairs and 2 lone pairs? That will be square planar. Okay, so these are the molecular shapes of the molecular geometry for different amount of bonding pairs and lone pairs, guys. So before I'm moving on to the ionic lattice, right? So please be clear. I'll make a small little summary here. If the question asks for electron pair geometry, okay, then we are just looking at the total number of electron pairs without considering number of bonding pairs and lone pair. Don't care. As long as I have 5 pairs, it will be trigonal bipyramidal. As long as there are 6 pairs, that will be octahedral. But then if they ask for molecular geometry, then we have to consider, out of the 6 pairs, how many of them are lone pairs and how many of them are actually bonding pairs. So that will actually lead us to, instead of octahedral, it will lead us to square pyramidal or even square planar. It depends on the number of lone pairs and bonding pairs. Can you get it clear? So we have electron pair geometry and molecular geometry. Of course, ultimately, we are aiming for molecular geometry because that is the actual shape of the molecules. All right, so next we look at ionic lattice. Now, what is that ionic lattice? How long is that already? It's 34 minutes. Okay, just now we were all talking about covalent bonds, covalent molecules, dative covalent bonds, and how they arrange. So covalent molecules will have different molecular arrangement based on the number of bonding pairs, number of lone pairs, right, on the central atom. In this case, we are looking at ionic lattice. Like I said, ionic lattice structure is not as simple as just Okay, positive, negative, positive, negative. I just put it in the cubic structure and that's it. This is ionic lattice. No, because ionic lattice also can be divided into these two. In fact, more than two we have, but at this level, we only learn two. I'm going to introduce only two. One is known as face-centered cubic structure, body-centered cubic structure. Now, one thing you can for sure, ionic lattice always arranged in a cubic structure, and then either face-centered or body-centered. What does that mean by face-centered and body-centered? Now, in short, right, face-centered we call it as FCC, body-centered we call it as BCC. That is just a short for it, the short name for that. And next, we look at how to differentiate them. For face-centered, in terms of the structure, right, you can see the arrangement in a cubic structure, and then you can see one atom on each face. In a cubic, we have how many phases? 1, 2, 3, 4, 5, 6, 6 phases, right? Each phases, you have a central atom here. That's why we call it as face-centered. At the center of a phase, you have atoms here. That's why it's face-centered. And then body-centered is, look at this cube. Okay, within the cube, you have an atom at the center, just at the center of the cube. Okay, sharing by 6 phases. It's not on like this. Each phase will have one, but this one is just one central atom at the center. So we call that as body-centered. And again, how can we tell? Are we supposed to look at the cubic structure image like given like this? No, we can actually do some basic simple calculations to identify whether these particular ionic compounds is actually arranged in a face-centered or body-centered cubic structure. Okay, now the calculation is as follows. It's very simple. So if it is a face-centered, what we're going to do is we're going to use the ionic radius of a positive ions divided by the ionic radius of the negative ions. So in this case, I'm going to use the ionic radius of sodium divided by the ionic radius of chlorides. And where can we get the ionic radius, ionic radii for all the ions? Data booklet. All right, so we just use the ionic radius of sodium divided by ionic radius of chloride. You'll get a value, right? You will get a constant. And this value, if it is less than 0.8, it will automatically be face-centered. Even though it is equal to 0.8, it's still face-centered. By right, it should be something like that. Okay, now, if you get a value more than 0.8, okay, more than 0.81 is considered more than. So that will be in BCC, body-centered cubic structure. So always remember the formula is as simple as positive ions radius divided by negative ionic radius. That will give you a value to know whether it is FCC or BCC. Okay, it's that simple. Now this is another 3D images that shows you how a face-centered looks like and how a body-centered looks like. Look at that, right? So this is how it looks like. And another thing is called coordination number. Okay, coordination number. Apparently you have two different coordination number for face-centered and body-centered. Obviously this is FCC, this is BCC. And what's the coordination number for FCC? What is the coordination number for BCC? It's very simple. Look, FCC means a coordination number means how many atoms are actually in contact with a central atom in this cubic structure. Let's say this structure, right? Okay, I presume that I have an atom, a red ball at the center, which we can't see it now because it's surrounded by the rest. And the one in red, 1, 2, 3, 4, 5, and the other one on the other side, 6. So you have 6 actually connected, touching the central red atom, right? The central atom. That's what we call 6:6 coordination number. This is for FCC. And for BCC, how many atoms actually in contact with it? The one in red, the one in blue. Sorry. Oh my goodness, I'm colorblind. The one in white. 1, 2, 3, 4, 5, 6, 7, 8. See that? These 8 white balls are actually touching to the central red ball, and that is the coordination number, which is 8 to 8. Okay, so coordination number for FCC is 6, 6. Coordination number for BCC is 8, 8. You can do more research on that. What is that coordination number of 6 to 6 and 8 to 8? I'll explain further in the tutorial, right? Okay, now let's look at superconductors. Now, what is that superconductor? Superconductors are, electrical conductors. And what's the difference between superconductor and normal electrical conductors? Superconductor is they can conduct electricity with no or zero resistance at a certain temperature. And that temperature, we call that as a critical temperature. Okay, the C here is critical temperature, TC, critical temperature. Now, different materials has different critical temperature. And having said that, not all materials can have its critical temperature, or shall I say, not all materials can achieve its critical temperature, because critical temperature can be as near as absolute zero. You see that? Can be as near as absolute zero. What is that absolute zero? Absolute zero is 0 Kelvin, which is negative 273 degrees Celsius. And it's not easy to achieve such a low temperature. We need a cooling agent to cool it down so that the materials will achieve its critical temperature. Again, different materials, different critical temperature. All right? And what are the cooling agents that we usually use? Helium. Liquid helium is the first one that we use, and because helium has a very low boiling point, so it is the best cooling agent. But helium is expensive, it's rare, right? And another one that replaces it will be slightly better, cheaper, is nitrogen liquid, or liquid nitrogen. Also, again, liquid nitrogen has a very low boiling point. When it has a low boiling point, meaning that it will have a cooling effect to the surrounding, because low boiling point means at a very low temperature they are still absorbing heat from the surrounding, so you will have a very good cooling effect to the surrounding. So that's why they can be used as a cooling agent. And imagine if you have a liquid nitrogen, I'm sure you guys seen it before. They use liquid nitrogen to freeze a creamy liquid and instantly turn it into an ice cream, right? So this liquid nitrogen, when you take it out at room conditions from the fridge, when you take it out, and then you can see a lot of fumes coming out, right? And that fumes is actually nitrogen gas, because they have such a low boiling point. So when they are up to these room conditions, let's say 25 degrees Celsius, it is good enough to vaporize all the liquid nitrogen. But at the same time, when they're vaporizing, when they're turning into gas, they are having a very good cooling effect to the surrounding, and that's why they can use it as a cooling agent. All right, liquid nitrogen is commonly used to cool down a material so that they can reach to its specific critical temperature, and then this material can conduct electricity without any resistance, and that's what we call a superconductor. And it will be good, it will be ideal if we have a material that can be a superconductor at room temperature. Isn't it best? So if you have something that can conduct electricity at room conditions without resistance, that will save us a lot of energy, because there is zero loss of energy to surrounding without resistance. Because resistance higher, meaning that you are actually using more voltage to actually transfer a current from one point to another, and that at the same time in the process will turn most of the energy or part of the energy into heat energy. Because of resistance, they turn it into heat energy and release to the surrounding, and that is an energy loss. So we try to make a materials that has a critical temperature which is equivalent to 25 degrees Celsius. All right, okay. Now the one that highlighted in blue, right? The one that highlighted in blue, that will be known as superconductive. Like they can conduct electricity at room conditions or ambient, not room conditions, sorry, it's pressure. At ambient pressure, they are superconductive, and of course temperature is another story. This is just in terms of pressure. So these are the potential elements for us to make a superconductive materials. Okay. Now this is one of the idea, and this is one of the example. Compounds such as 1, 2, 3 superconductors. That's the name. And why is it 1, 2, 3? Because they're using 1 yttrium, 2 barium, and 3 copper to combine with outnumber of oxygen, various number of oxygen, to form a structure, to form a compound that can actually conduct electricity with 0 resistance. See that? So what is the critical temperature of this compound? This compound has a critical temperature of 92 Kelvin. All right, it's considered really good. All right, and then hence liquid nitrogen with boiling point of 77 is still lower than 92, right? So liquid nitrogen still having a lower boiling point than this compound, so they can act as a cooling agent, which is cheaper compared to helium. All right, and the properties of superconductors depends on its structure and the packing of its atom or ions in a crystalline form. So it depends on how they arrange. The arrangement of the atoms or ions in a structure can actually give us a superconductor. So based on the materials highlighted here, we can choose them and try to manipulate, try to change the arrangement, try to give them into different ratio. Just now was 1, 2, 3, right? 1 yttrium, 2 barium, and 3 copper. What if I change them like 2 yttrium, 4 barium, and 6 copper? They may give us another superconductor. So we have to play around with that, and that's what's happening in the research. And we are trying to play around with the materials so that hoping to get a better invention or a discovery so that we can get a better future or better properties of a material. Okay, so next, that's it for a superconductor. And then we have semiconductor. Now, when you see the word semiconductor, I'm sure you will think of silicon, right? Silicon is a well-known semi-metal or semiconductor. And what is that semi-metal and semiconductor? Semiconductor will have a conductivity that is slightly lower than a normal conductor, but higher than an insulator, of course, right? So what makes them conduct electricity? This only happens when we provide energy input, we heat it up. So therefore, a semiconductor can only conduct electricity or with a better conductivity with an increasing temperature. They need to increase the temperature before they can actually get a better conductivity. So silicon, when you heat it up, they can actually give us a better conductivity than an insulator. Okay, so conductivity increases with increasing temperature. And why does this happen? Because silicon is supposed to be arranged in such a way, right? Silicon is same as carbon, has 4 valence electrons. So in a lattice structure or in a solid structure, they form bonds like that. Each silicon should form 4 bonds like that, right? They're continuous. So look at this. I'm forming 4 bonds. But when you provide heat energy or high temperature, this heat energy may, okay, break some of the bonds. When they break the bonds, what's going on, guys? When you break the bonds, you actually release out some electrons. Let's say a share pair of electrons here, a share pair of electrons here. When you break them, these 2 or these 4 electrons are free to move when you break the bonds. You're not breaking all of them, but some of them. So when these electrons are free to move, no longer bonded, then they can carry charge. And that is why you can have a conductivity at that point. All right? So next, move on. We have a few different types of semiconductors, right? We have P-type and N-type. Now, this diagram is actually to show us the energy gap or the band gap between a metal, which is a conductor, semiconductors, and insulator. Look at that. The empty and the filled band. Now, the filled band is actually full of valence electrons. The empty is orbitals. You learn about orbitals, previous topic, orbitals with no electrons. So when you have orbitals with no electrons and then combine with orbitals with electron, the valence electrons, then you can actually promote conductivity. Look at that. If it is a metal, the empty orbitals and the filled orbitals are actually overlap. When the overlap means the electrons from the filled orbitals can actually jump up to the empty orbital, jump to the empty orbitals, and then move around, up and down. So when the electrons jump up and allowed to freely move, that it means it can conduct electricity easily. So this is a metal because the filled band with electrons and the empty bands are overlapping, are together. But semiconductor, you have a small gap here. So therefore, when you increase the temperature, you provide energy to those electrons here to jump over this small gap into this free empty space. And when they are at this free empty space, they are free to move around, meaning that they can carry charge, they can conduct electricity. And for insulator, obviously the gap will be big. Even though you heat it up to a temperature, even though you melt it or whatever, the electron will still not gaining enough energy or not sufficient energy to jump across. They can't jump into the empty orbitals. So therefore, no conductivity. And that's the gap difference between metal, semiconductor, and insulator. I mean, metal here is conductor or even superconductor. It depends, right? So, semiconductor continues from here. Silicon and germaniums are similar to diamond, but bonds are weaker, so that I can use a temperature to break some of the bonds so that the electrons are breaking free. That's what I explained just now. When they're breaking free, the electrons are free to move. At the same time, you're creating holes, positive holes. So you have positive holes. Here, you have electrons free to move. Electrons here, holes here, holes here, holes here. So the electron can jump into this free hole and jump into here and jump into another electrons and push this electron over to another holes. So they allowed spaces. The positive holes actually considered as space for the electron to move around, because in a solid state, they are usually very compact, no space at all to move. So when you have positive holes, when you have break-free electrons, these two combinations is the best for conductivity. And how can we actually increase the amount of electrons or the amount of positive holes? We can dope it with different elements. So if you're doping it with elements of extra electrons, now let's take silicon as an example. I have 4 valence electron for silicon to be a semi-metal. Then on the other group, on this side, this is group 4, and this is group 5, and this is group 3, right? So if you're doping it with group 5 element, let's say phosphorus, you're putting this phosphorus into silicon. In other words, indirectly, you're providing them a surplus of electrons. Why? Because phosphorus should have 5 valence electrons. When you put phosphorus in, you would definitely, let's say, a silicon, right? Combined with, supposed to be silicon, all of them, but then suddenly one of them changed into phosphorus. What will happen? Now, 4 electrons for silicon, 5 for a phosphorus. So you have 1 extra electrons that are not doing anything. See that? So you have 1 extra electrons here, and these extra electrons, without any temperature increase, I already have 1 free electrons free to move. And that will actually increase the surplus of electrons. And this is what we call N-type. All right? And then for P-type semiconductor, like gallium from group 3, let's say again the structure silicon here is supposed to be bonded with 4 silicon as usual. But then when a silicon, a gallium is actually added into it, let's say a gallium added here, G. G should have how many valence electron, guys? Only 3. So you can form 1, 2, and 3. So this one, you can't form a bond because you have insufficient electrons. And this part will give you a hole, a positive hole, or just hole. In fact, it's not positive, just hole. So this empty space will allow any break-free electrons to jump into it so they can move around throughout the structure. And this is what we call a P-type semiconductor. All right, and next one is the PN junction as well as the photovoltaic effect. You know, these two, I'll leave it to you guys, and then let me know if you need help on that. I can explain further in the tutorial sessions. And that's all for the summary video for this topic for this week. Thank you so much, guys.